So we have a quick little lesson today as we wrap up Unit 1 on relative motion and velocity vectors. So we'll start off with a little concept question. This is a review. A person starts a position of 3.0 meters and then moves to a position of 9.0 meters before turning around and finishing at position 2.0 meters. Displacement for this trip is what? Hopefully you can figure it out in your head. Here's a little sketch, and we're going to solve it together. 0.3 meters to 0.9 meters. That's your first that's your first displacement. So you can think of a little vector that would be 6 meters long. Then you're going to come back a total of negative 7 meters because you're going to end up at 2 meters. So what is your total net displacement? Well, you just add the two vectors together and you get negative 1 meters. So that was the correct answer, answer B. All right, moving on. So we're going to talk about applications of vectors, namely with relative motion. So we're talking about velocities here. When you're talking about velocities, it really depends on your frame of reference. So if you think about walking on a train, you could have motion, the train could have motion, and then you, as you're walking, could have motion. So are you walking in the same direction as the train? Are you walking in opposite directions of the train? Are you standing still? So it depends on what's moving, what's standing still, and what your frame of reference is. So some examples of one-dimensional relative motion problems are problems where you're walking on a train, those little people movers at the airport, those escalators that are not climbing stairs, and running on a treadmill. Think about what's happening there. You have the treadmill's going one direction and you're running, and yet you stand still. Okay, so we're going to use some terminology to help us keep track of what's happening with relative velocities. So if we talk about a little car on a piece of foam core, and the foam core relative to a big lab table, we want to figure out what's the motion of the car with respect to the table. So we use some nomenclature. If we say V sub CB, V sub CB, that would represent the velocity of the car relative to the board. So we have that little C and the B, car relative to board, and you'll see that right here. If we have the velocity of the board relative to the table, that would be board relative to table. That will give us, if we add those two velocity vectors together, the velocity of the car relative to the table. So CB goes to BT, and you form CT, so the B in the middle kind of drops out. So let's take a look at what we're thinking of here. You have a car on a moving board. So here's a little sketch. Here's the car. And the car is moving on the board. So it's that little motorized battery-powered car, and the car can move on the board. But then you also have the board moving. So if the car is moving on the board, and the board is moving relative to a table, then you can imagine that the car relative to the table is going to be moving really fast if they're both moving in the same direction. And we see that from the vector addition scenario. So here's your car on the board, and the board is moving with respect to the table. So your total velocity of your car with respect to the table is really big because you have to combine the velocities of the board and the car to get the relative velocity of the car versus the table. By that same token, we could have the board switch direction. So we could have, in this case, the car is moving to the left, but the board is moving to the right with respect to the table. So now the net velocity of the car with respect to the table becomes much smaller. Even though the car relative to the board is going to the left, the board is moving to the right, so a net velocity of the car with respect to the table. So that's how we can do some simple vector addition to find relative velocities. Now again, this is sort of one-dimensional, but we can now extend this into 2 dimensions. So in this case, if we have our same car and board and table, but this time we're going to have the car moving to the left as it always has, but this time the board is going to move perpendicular to the direction of the car. So you have the car moving to the board this way, but then the board is going to be moving in a perpendicular direction. You say, well, what is the velocity of the car with respect to the table? Well, it's going to be this net larger velocity. Is going to be this one right here. That's going to be your velocity of the car with respect to the table. So we had to use vector and vector math in order to find that net velocity. So you'd have to use some Pythagorean theorem, and you'd have to use some trig to get the angles, etc. So common examples of two-dimensional are airplane problems. So let's set one up real quick. Here's your airplane, and it is going, the velocity, talk about the velocity of the plane with respect to the air. But then the air might be moving, so we'd say, well, there's the velocity of the air with respect to the ground. So then the question becomes, what is the velocity of the plane with respect to the ground? So if we add those together, you're going to get the velocity of the plane with respect to the ground. Okay, jumping ahead, river problems, boat and river problems, classic relative velocity type problems. So you have your boat and you have your river, and your boat, when you paddle your boat relative to water. So you'd say, what's the velocity of the boat with respect to the water? But then the water might be moving. And so you say, well, what's the velocity of the water with respect to the shore? And then the question is, what is the velocity of the boat with respect to the shore? Well, you can imagine it's going to be traveling at an angle such as this. So velocity of boat with respect to the shore. To find that velocity, you're going to have to use vector addition using Pythagorean theorem and trig. So let's take a look at an example problem. Here we go. A person is rowing east at 4.0 meters per second relative to the water in a river. The current flows south at 2.8 meters per second. Find the magnitude and direction of the boat's velocity relative to the shore. Okay, so here we go. Let's identify our vectors. We're going east, so we have the velocity of the boat with respect to the water, and it's going to be 4.0 meters per second to the east. Now, I put a little compass so I can keep track of what direction. So to the right is going to be our velocity vector of the boat with respect to the water. Then we have the water with respect to the shore is going to be 2.8 meters per second, and that's going to be in the south direction. So we have a vector going down. Now we want to combine those two vectors to find the net velocity vector, the relative velocity of the boat with respect to the shore. So we do that using Pythagorean theorem. Velocity of the boat with respect to the shore is square root of 4 squared plus 2.8 squared. I throw that into my calculator and I get 4.9 meters per second. And then I need to find theta. So I'm going to use the tangent, inverse tangent function. Inverse tan of theta is going to be opposite over adjacent, which is 2.8 over 4.0, and the units are going to cancel. So I'll find that theta is 35.0 degrees. 35 degrees of sig figs. Now, how do I specify that direction? Well, if 4.0 meters per second is to the east, and that relative velocity of the boat with respect to the shore is going to be 35 degrees south of east. And that would be your final answer. Oops, sorry, went too fast. Okay, now, so that'll give you a head start to do the problems for the homework tonight. I want to take you through one more little projectile problem practice. Hopefully you're getting good at these now, because tomorrow in class you will be doing an activity where you have to determine the correct placement or landing of a projectile. So it's similar to this. Here we go. A cat is chasing a mouse on a slippery table. Just as the cat is about to catch the mouse ducks to the side and the cat cannot recover, sliding off the table into the air. If the cat leaves the table with a horizontal velocity of 1.5 meters per second, the table is 1.2 meters tall. First, how long until she hits the ground? And then second, where would the dog want to be so he can catch the cat precisely? Okay, so let's take a look at this scenario. What we know is that the velocity initial in the x direction is 1.5 meters per second. And I'm putting in red what's happening in the y direction just to kind of keep it straight. Because we basically, when we're doing projectile motion problems, we keep track of the x equations and the y equations separately. Now, delta y, that's the total distance that the cat has to travel in the vertical direction, is 1.2 meters. So, the first part says, how long until she hits the ground? Well, if she's got to fall 1.2 meters, it doesn't matter whether she has horizontal velocity or not, it's going to take her a certain amount of time, the amount of time that it would take gravity to pull her down. So let's figure out what that is. So we'd say delta y is 1.2 meters, and that's going to be equal to v sub 0 in the y direction times t plus 1/2 at squared. Now I decided to determine that up is positive, so I said that the displacement down is negative 1.2. And if I do that, then first of all, the v sub 0 y, it has no initial velocity in the y direction. I'm not throwing it down. I'm not throwing it up. The only component of velocity is in the x direction. So that first term v sub 0 y is going to go to 0. Now I've got to add in gravity, so I say minus 1/2 gt squared, or 9.8 times t squared. I've just said, remember I said that up is positive, so gravity is going to act down. So now I've just got to solve that equation for t. With my calculator, I go through that process, and I get that t is equal to 0.5 seconds. 0.50, it's actually 0.49999. 0.50 seconds. So it takes half a second for the cat, once it slid off the table, to fall to the ground. Well, then the next part of the question is, where would the dog want to be so he can catch the cat precisely? Well, now we know that the cat's going to be in the air for 0.5 seconds, so how far horizontally is the cat going to travel? What is that delta x in order for the dog to place himself in the right location? Okay, so, well, we know it's going to be traveling for half a second. We have our kinematics equation in the x direction. In this case, the acceleration in the x direction is 0, so our equation just reduces to delta x is equal to v sub 0x, the initial velocity in the x direction, times t. Now we're given that v sub 0 in the x direction is 1.5 meters per second, so 1.5 meters per second times the time, which we found just a minute ago, is 0.5 seconds. So the total distance it's going to go is 0.75 meters. So that's where the dog would want to locate in order to catch the cat. Okay? That concludes our lesson for today.